So here's your introduction to related rates. The best thing about related rates is maybe the worst thing for some people and it's that related rates always has some sort of picture associated with it, which is almost always, which makes it so fun because we go back to our days of art class and drawing circles and spheres, and we are embarrassed when they don't look perfect, and we're just going to have to get over that. So here is a sphere. This is going to be a balloon, and let's say it's a perfect sphere, and we are pumping air into it from this, let's say this pump right here, and we are pumping air into it at a certain rate. Well, what rate would make sense? What kind of units? Well, we're pumping it in a certain number of cubic inches, let's say, per minute. And I hope this dimensionally makes sense. So here it is in calculus. In terms, we're looking at the change in volume with respect to time. That's what the pump is providing. A certain rate. So what kind of questions would calculus help us answer? Given a certain rate that we're pumping the air in, we can also find out how fast the diameter is changing with respect to time. And so let me write that. The change in the diameter with respect to time. This is going to be one of the questions we're going to answer. And intuitively, when you think about this balloon, when it first starts out and we're pumping this air into it at a steady rate, the diameter is going to be increasing quite quickly. And then once the balloon gets really large, the change in diameter with respect to time is going to be lower. It's going to the diameter will be diameter growth will be slowing down. Okay, so let me label that D just so we see that. And here it is formulaically. We know that the volume of a sphere is 4/3. That's a 4/3 pi r cubed. And in terms of diameter, since the radius is just 1/2 the diameter, we could just write this as V is equal to 4/3 pi d over 2 cubed. Now, really like to think of these volume is a function of time. So I kind of like to think of this little tiny, maybe get a little smaller brush here, little tiny t down here. V is a function of time, and d is also a function of time. So you can see the smells of implicit differentiation. It's the reason we came right after this comes right after implicit differentiation. Okay, so what's another good related rates problem that we're going to be able to answer? So if we had a building like this, and we had a ladder leaning up against the building for whatever reason, it has a ladder of length L, which is going to be constant throughout this problem, and some joker was taking the bottom of the ladder and he was sliding it out here, and this distance right here, let's say let's call this, it's the lateral distance, this is x. He was pulling the bottom of the ladder out at a certain rate. So so the change in x with respect to time is some rate. He's just sliding it out. Again, why, I have no idea. We could answer the question. Let's suppose we had you see this ladder forms an angle theta with the building. We could answer the question of how fast the theta is changing with respect to time. And right here, you should, since this building is, it's not the Leaning Tower of Pisa, we're going to form a right triangle right here. You can see this. You can see this. This is going to be a right triangle, and if we're here at theta, hopefully you can see that the sine of theta, which is a little, I'm just going to, theta is a function of time, right, is equal to x, which is also a function of time, over L, which is just a constant. Now, when we're looking forward to where we're going, you can see the, hopefully you can see the implicit differentiation that has to go on here. We're going to take the derivative with respect to time of the whole thing, and you can see that dx dt happening over here, and this d theta dt happening over here. Okay. And those are two great problems. We're going to do lots of applications and draw lots of great pictures like that.